Hello, am I audible to you?
Hello, Dr.
Hi,
Pulkit Kumar. How are
hi,
you?
Kumarjit. I'm good. What about you?
I'm also doing good, and it's
How's
after a
that?
long time.
Yeah, sure.
So, we'll wait for a few more minutes, then
Yeah, sure.
we'll start. Okay. Thank you for joining.
How's your research going on?
Just going on marathon. So, good evening, everyone, uh, and good morning to Dr. Pulkit Kumar. So, like today, we are going to start the session that is a talk on mathematical solution for elastodynamic problems. So before starting, I'd like to introduce myself. I am Kumarjit Ray, a PhD scholar in the Department of Computer Science and Engineering in IIT Kharagpur. And also I am the chair of Computer Society Student Branch Chapter in IEEE Kharagpur section. So this is our second talk in this year, second technical talk. So in today's talk, before starting, I'd like to uh, introduce our speaker, Dr. Pulkit Kumar. He is the research scientist from Center of Non-Destructive Evaluation, CND, Iowa State University, Ames, Iowa State, and in USA. So he has done his PhD in applied mathematics from IIT Dhanbad, and his main area of research is wave propagation, solid mechanics, elastodynamics, and non-destructive evaluation with specific applications in composite materials. His professional experience includes postdoctoral research associate in CND, Iowa State University, and also he was the assistant professor in Shiksha Anusandhan University, India. He has also done his postdoc from IIT Delhi. He has authored more than 19 SCI journal papers and contributed to several conferences. Currently, his citation index is 259 and it is growing continuously, and its H index is 11. His software proficiency includes Abacus, Mathematica, and MATLAB. And he has some ongoing projects which includes ultrasonic testing, characterization of complex microstructures in titanium alloys, then model assisted probability of detection, then NDE modeling of ceramic matrix composites. He has also few professional memberships, like life member of several scientific societies, and also he is the reviewer of more than 20 journals. His main research includes interest is focuses on advancing NDE techniques, then bridges the gap between theoretical modeling and experimental validation, and he also in his research addresses the critical challenges in aerospace, automotive, and electronic applications. So before starting the talk, this is the general instructions for all the attendees. Please keep yourself muted during the talk, and also please wait till the end of the talk to ask any kind of question. There will be extra Q&A session at the end of the session, and an attendance sheet will be distributed, and you can note your attendance there. And also you may type your queries in the chat box also, and we'll be taking a group screenshot of the event at the end, and at the time you can turn on your cameras if possible. So thank you again to all the participants, and also I'd like to thank Dr. Pulkit Kumar for joining us. And now I'd like to request Dr. Pulkit Kumar, you can start the session, you can start the talk. So Dr. Pulkit Kumar.
Now is it visible?
Yes, it is visible.
Thank you, Kumarjit, for this kind introduction, kind and broad introduction. So I truly appreciate this opportunity to present my work today, and I would like to extend my gratitude to IEEE Computer Society student chapter at Kharagpur, and to all of you for joining this talk. So basically my background is mathematics, so we'll discuss something about the applied mathematics, some physics. So now suppose if a material, what is the elastodynamic wave? So suppose if a material has the property of elasticity and the particles in a certain region are set in a vibratory motion, so an elastic wave will be propagated, right? So before going into this talk, I'll give a brief intro of my university, where it is. So we are here at the Iowa State University, located in Ames, Iowa, which is the Midwest region of the United States. Specifically, Iowa is situated in the northern part of the Midwest and is often considered part of the central United States as well. So now talk about the birthplace of the computer. So right here at the Iowa State University is known as the birthplace of the computer. So between 1939 and 1942, Professor John Atanasoff, a professor of physics and mathematics, and his graduate student Clifford Berry, an engineering student, developed the world's first electronic digital computer. So Atanasoff, often called the father of the computer, sought a way to solve complex mathematical problems faster and more accurately. So together with his engineering graduate student Clifford Berry, they built a machine that would lay the foundation of the modern computing. So this groundbreaking achievement took place right here in Ames, Iowa, making Iowa State University not only what can we say hub for research and innovation, but also a proud part of the computing history. So now let's take a closer look at the key features of the Atanasoff-Berry computer ABC. The original Atanasoff-Berry computer is no longer functional. A replica was built in 1997, bringing this groundbreaking piece of technology back to life and showcasing its historical significance. So unlike the computer we use today, it has no mouse, keyboard, or a screen. It was built with rotating drums for memory, glowing vacuum tubes, and read-write system that use cards with marks to record data. The computer itself was about the size of the large desk and weighed 750 pounds. So now, as for the budget, the initial cost to build the machine was $5,330, and which adjusted for the inflation would be about 96,000 in the today's dollar. So Iowa State University is having a supercomputer, which is, and we call it the NOVA supercomputer, with a high performance computing system with 38,000 CPU cores and nearly 200 GPUs. So NOVA powers breakthrough the material science, ultrasonic ND, and computational modeling, making supercomputing accessible for all ISU researchers. So here's my center where I work. This is the Center for Non-Destructive Evaluation. So to know about the CND, here's a link of the video. So I'll play this video, and this is a 5-minute video. So you can know a little bit about my center, what we do here. So now let's watch. What is this? Yeah, so this is about my center. So now I am moving to my talk. So basically, in this talk, I will present the recent analytical studies on two key topics in wave material interaction. So the role of the stress intensity factor in crack propagation within anisotropic materials and the diffraction of magnetoelastic plane waves by rigid strip in a reinforced material. Basically, my background is mathematics and applied mathematics, and I am inclined towards the physics. So now I will discuss more about the applied maths and the physics. So for some of the audience, it may be a little bit hard to understand, but be patient. We'll have something. So this work contributes to advancing our understanding of fracture mechanics and wave interaction in anisotropic materials. And these studies provide deeper insight into the fracture mechanics, wave interaction, material behavior, or which are crucial for application in structural health monitoring, ultrasonic ND, and the advanced composites. So this work provides analytical solution, and now we aim to address challenges in wave propagation and material failure prediction. So this presentation is structured as uh, like elastic wave and the seismic waves, and we will discuss something about the what is the crack in the fracture mechanics, that is the modes of the crack and the stress intensity factor and its role predicting material failure, and Griffith crack in a crystalline monoclinic layer, and diffraction of plane waves by a rigid strip. It will be good to have the laser point. Yeah. So the elastodynamic problem is something that deals with the elastic wave propagation. If you have any dynamical system, and it will concern with the elastic waves. So there are several types of elastic waves like bulk waves, interfacial waves, and the surface waves. These waves can be understood in the context of the seismology. So if you have an earth structure and somewhere on the surface we have a seismic station, or seismograph is there where we record all kind of the readings, and somewhere in any part of the earth there is an earthquake source. So this is the starting point of the earthquake, maybe due to some tectonic movement, or maybe another kind of the artificial explosions. So seismic waves will be generated. So the seismic waves are the bundle of elastic strain energy that propagates outwards or along with its surface layer from the seismic source, usually during an earthquake or man-made explosions. So the propagation characteristics of seismic waves provide valuable information about the interior of the Earth, and the classification of the seismic waves depends on the trajectory of the particle motion, physical properties, and the propagation characteristics. So the waves are basically characterized into two types: body waves and the surface waves. So body waves, it is clear by the name. Body waves travel through the body. Uh, Body waves travel through the body, through the interior of an elastic medium, and reaches to the seismic station. And the the surface waves, these are the surface wave propagates along the surface of the medium. So now we have two types of the wave signal received at the seismic station, at the small one and you can see that of the bigger one. So you can see which one is faster. Obviously, the body waves are faster. Uh, because body waves are of higher frequency than the surface waves. So the body waves are divided into two types of waves: primary waves and the secondary wave. So the first graph is having the first signal of P wave, which is coming faster than the secondary wave. Secondary waves cause a structure vibrate to side, and S waves are divided into two kinds of the waves: SH wave and the SV wave, shear horizontal and the shear vertical. the vibration in the if the particle motion in the horizontal way, then we call it the shear horizontal. If the particle motion in the vertical way, we call it the shear vertical. So all the destruction you see is due to the surface wave, because the surface wave produce more ground movement and travel more slowly. So they take a longer time to pass, just as a wave interaction at the cracks and defects significantly impact material strength. So now see the oscillation pattern. You will understand why the surface waves are more destructive, because the amplitude is high. So the effect of surface wave decay as the depth increases. And the surface wave can be divided into two types of the prime categories, love wave and the Rayleigh wave. So the love wave are the horizontally polarized surface waves named after the famous British mathematician A.E.H. Love. So this particular type of surface wave exists and propagate only in the structure consisting of a layer of finite width overlying a semi-infinite medium. And for the Rayleigh wave, the Rayleigh waves are the elastic surface waves that are elliptically polarized in the plane, which is determined by the normal to the surface and by the direction of wave propagation. So the Rayleigh waves are a combination of both longitudinal and the transverse wave. So you can see here the velocity of the P waves, which are known as the primary or compressional waves. So these are the fastest elastic waves and propagate through the material. So this was the destruction part of the waves. Now, if we talk about the some constructive part of the wave phenomena, so we are all using touch screens, gadgets like mobile phones, iPads, or anything. So those have elastic material inside them to propagate the elastic wave. When we touch the screen, an elastic wave works to scroll the screen. So this phenomena can be employed in the design of surface acoustic wave devices to enhance their frequency, and such type of sensors are using in the car vehicle. So basically what we will do, we will construct some mathematical model, that will the boundary value problem. Then we will assume a time harmonic solution. We'll try to eliminate the arbitrary constants with the help of the boundary conditions. Then we will deduce field variables and the related expressions. And after that, we will do some numerical study. So now the fracture in the elastic media. So what happens when a sudden disturbance or a high intensity load is applied to an elastic body? So it can generate internal stresses leading to the formation of the cracks or micro cracks. So it generates elastic waves that propagate through the material or the medium. And if the stress exceeds a critical limit, it can lead to the formation of cracks, or you can say that the micro crack. So Irwin, 1957, first explored the behavior of the cracks in elastic body and suggested 3 different loading modes of crack with an idea about applying force to enable a crack to propagate. So there are 3 modes of crack: mode 1 crack, mode 2, and mode.
ওই প্যান্টটা অন্তত খোল, খুলে খোল প্যান্টটা।
Okay, so the mode 1 crack is the opening mode, or we can say that there is a sliding crack. So the very important part of the crack study is the stress intensity factor. So the stress intensity factor is used to predict the stress state or the stress intensity near the tip of a crack or notch caused by the mechanical loading or the residual stresses. So basically residual stress refers to the internal stress that remains in a material after the external forces are removed, often due to manufacturing process like welding, casting, and then cooling. So these stresses can be influenced by the behavior of crack or any kind of the notches in the material. So the stress intensity factor depends on the applied stress, crack length, and the specimen width. Specimen means suppose if we are having any kind of the sample or whatever. So this stress intensity factor depends on the sample geometry, the size, and the location of the crack. And the linear elastic theory predicts the stress distribution sigma ij near the crack tip in polar coordinates theta with origin at the crack tip has the form of this. So it is theoretically constructed usually for homogeneous linear elastic material and is useful for providing a failure criteria for brittle materials. So the stress intensity factor, three modes of crack is denoted by K1, K2, and K3. And the term sigma YY represent the normal stress ahead of the crack along the crack plane. And K2 is for the sliding mode, and now here R represent the radial distance from the crack tip. And now the next one for the K3, that is the tearing mode. So these all are find out by Irwin. So there are so many named crack, but in this presentation I will focus on the Griffith crack, penny-shaped crack, or some different kind of the cracks are there. So now for the Griffith crack, the total energy is equal to the strain energy and the surface energy. So the crack propagates when the release of the elastic strain energy exceeds the energy of the form. A new crack, what we call the exceeds the energy required to form new crack surfaces. So mathematically, Griffith's energy balance is given by is equals to GDD of DDA of U, which should be the greater than or equals to the critical energy. So here G is the energy release rate at which the elastic strain energy is released per unit crack area, and U is the elastic strain energy stored in the material, and A is the crack surface area, and GC is the critical energy release rate or the fracture toughness. So here we'll discuss about the analytical study on the stress intensity factor due to the propagation of Griffith crack in a crystalline monoclinic layer subjected to punch pressure. So this work is published in Fatigue and Fracture of Engineering Materials and Structure. So now let us consider an elastic plane problem of a moving Griffith crack of finite length 2L influenced by a propagation of plane waves placed in a mid-plane of the crystalline monoclinic layer of finite width 2H and of the infinite extent. So the considered layer is punched parallelly on the bonding surface in both the sides at the corresponding location of the moving Griffith crack. So now a coordinate system OXYZ is chosen in such a way that the layer is defined by define the whole plane, and y-axis is lying between minus h to plus h, and the crack is defined by mod of z less than equals to l at y equals to 0. So it is assumed that the crack is moving along the parallel punch pressure acting on the bounding surface of the layer with a uniform speed c along the z-axis. So the stress-strain relation for a y-cut crystalline monoclinic layer that reveals the monoclinic symmetry in which x-axis represent the diagonal axes are defined by equation number 1, where tau xx, tau yy, and tau zz are denote the normal stress component, and these denotes the shear stress component. And similar for these exx, eyy, and ezz represents the normal strain component, and the rest of these represent the shear strain components. And these Cij indicate the elastic constants of the material. So the equation of motion for the elastic disturbance in a crystalline material without body forces is given by equation number 2. So the plane strain deformation condition for moving crack because of the propagation of plane wave in a crystalline monoclinic layer which is parallel to the YZ plane is defined by equation number 3. And the question may come into the mind, how are two displacement components are possible, right? So for pure plane waves in isotropic materials, one displacement component is sufficient. But if we're dealing with anisotropic media like monoclinic materials, so two displacement components are possible. Here we are dealing with the two displacement component V and W. UV and W are the three displacement components in the direction of X, Y, and Z axis. So now on substituting all these stress strain relation, plane strain deformation condition in the equation 2, and now we will have the non-vanishing coupled equation of motion like 4a and 4b. So now what will the main task? Our main task will be to make the problem static, that is to reduce the mathematical complexity. So it is supposed that the Griffith crack is moving with a uniform speed c, and the considered model of the system XYZ is extended by a convecting frame of reference small x, y, and z. Here you can see. After a certain, because the crack is moving with uniform velocity speed c, so after time t, it reached here, and now we are. The new convective frame of reference will be small x, y, and z. So now, therefore, in view of the Galilean transformations, we have equation number 5. This is known as the Galilean transformation. So using this Galilean transformation, the coupled equation of motion becomes static, which is defined by equation 6a and 6b. Now, for the boundary conditions, we will go back to the geometry of the crack propagation again here. So after a certain time t, the moving crack is defined by mod of z, small z less than equals to L at y, small y equals to 0, so which is subjected to internal normal traction P of z, and the normal punch pressure, this punch pressure, we denote it by the QZ, is acting at the mod z less than equals to L on the both the surfaces y equals to h and y equals to minus h, so which is defined by here. And because of the punch pressure, we consider the surface becomes rigid. So that as the surface becomes rigid, the displacement in this part will be 0 because there will be no deformation. So that's why the displacement is considered at the 0 where we consider the punch pressure, because we can see at that we can see that at that place the surface becomes rigid, so that's why we considered V and W is equals to 0, and the stresses is 0, and the next one is the not because of the normal traction or the normal punch pressure is equals to the minus Q of Z, and the boundary condition at y equals to 0 at the similar one. So now we can say now these are the boundary conditions, and the solution of equation 6 may be considered in the form of the Fourier integral, which is defined by equation 9a and 9b. So now The question may arise here why these equations are expressed as an integral representation using Fourier and cosine transforms. So the integral transform method, Fourier type representation, helps to convert partial differential equations into the algebraic equations in the transform domain. And A and B are known as the unknown functions in the transform domain that describe the displacement field, and they depend on the spatial coordinate y and the Fourier transform variable. So for v, y, comma, z out of the plane component, a sign transform is used to satisfy the anti-symmetric boundary conditions. And for w, y, z, in-plane displacement component, because of the in-plane displacement component, a cosine transform is used to satisfy the symmetric boundary conditions. Now, with the add of the equations 9a and 9b and the equations 6a and 6b yields the following expressions to govern the functions a's and b's, which is represented by equation number 10a and 10b. And now the solution of these equations can be written in the form of the equation 11a and 11b, where gamma 1 and gamma 2 are the positive roots of this biquadratic equation 12, and the beta is the phase velocity of the wave. So this paper is full of mathematical expressions, so I skipped most of the mathematical parts of the work. So if anyone wants to see, I can share the published work. So now let us consider the edge y equals z equals to 0 of the moving crack is loaded at z equals to z0 by a force of the intensity P, which is constant inside the crack front, and z0 is any point into the layer. Therefore, I'm assuming the case of the point loading as P of z equals to P and the drag delta function z minus z0, where this is the drag delta function. So now this is considered because of the mathematically convenient for solving the integral equations. So a point load applied to near to the crack tip increases the stress intensity factor, making the crack more likely to propagate. As Z0 moves closer to the crack tip, the stress intensity factor increases. So this is the required expression for the stress intensity factor at the tip of the moving crack with constant point loading in a monoclinic crystalline layer of a finite width, which is punched parallelly on the boundary of the layer and the corresponding location of the crack due to the propagation of plane wave. So when we reduce the elastic constant of the monoclinic material to the isotropic material, that is the easiest one, from the 13 elastic constants to 2 elastic constant and made free from the punch pressure, the equation reduces to the equation 16, and now this results found in the well agreement with the result established by AK Mull for the isotropic cases, which validates our mathematical model. So for the numerical study of the established analytical result, so we consider the elastic constant values for lithium niobate and lithium tantalate with the monoclinic geometry. And we studied the parameter considered in our problem, like velocity of crack, punch pressure, and the crack length, different position of point loading. So in these figures, the first one is the is for the lithium niobate, second for the lithium tantalate, and the third one for the isotropic case. So curves 1, 2, 3 shows the results for the increasing punch pressure. These figures indicate that the stress intensity factor for a moving crack located at in the center of the layer increases as the punch pressure of the layer boundaries increases in all the cases. And you can see the stress intensity factor is higher in the isotropic material medium. Now for the crack length, so now this figure shows the effect of the crack length on the stress intensity factor. So from the figures, we can see the crack length increases the stress intensity factor. This effect is observed in all three materials like lithium niobate, lithium tantalate, and the isotropic materials. As you can see here, the impact of the crack length on stress intensity factor is more significant in isotropic materials again as compared to the rest of or the other two. So now for the point loading, the figure also show the stress intensity factor increases as the point load moves closer to the crack tip. At first, the stress intensity factor rises, but as the load gets closer to the crack tip, the increases becomes smaller. Why is it? Because as the point load moves closer to the crack tip, it increases the stress concentration, making the crack more likely to grow. So these are the key findings of this study. So the stress intensity factor decreases continuously as crack velocity increases due to the plane wave propagation, but later on it settles down to 0 when the velocity of crack approaches to the velocity of the wave. And the longer crack exhibits the higher stress intensity at the crack tip. And for the moving the point load closer to the crack tip increases the stress intensity factor. And the stress intensity factor is higher in the isotropic materials than in the monoclinic layers. And if you talk about among the monoclinic layers, the lithium tantalate shows higher stress intensity factor than the lithium niobate. So now we move to the next part of the talk. So the diffraction of magnetoelastic plane waves by rigid strip in a reinforced medium. So before going into the main problem, first we will discuss about some basics of the reinforced material and the magnetoelasticity. So there is a reinforced material along the direction of a unit vector A is defined by equation number 1. So where tau ij are the stress components, lambda, alpha, and beta are the elastic constants. A is the unit vector representing the direction of the reinforcement with modulus 1. And Eij are the strain components. Mu L and mu T are the shear modulus along longitude and the transverse direction. So the electromagnetic field equations follows Maxwell's fundamental equations, and Ohm's law in the generalized form for a deformable body is defined by equation number 2, where B is the magnetic induction, E is the electric intensity, H is the magnetic intensity, mu is the magnetic permeability, J is the electric current density, and sigma indicates the electric conductivity, and UI, this UI represents the component of the displacements, and T represents the time. So the governing equation of motion for the disturbance of elastic waves in a conducting material with an electromagnetic force, which is known as the Lorentz force, which acts as the body force, is represented by equation number 3. So this is the model of our problem. So an elastodynamic problem for the diffraction of magnetoelastic plane waves, which incident normally on a rigid strip of finite length 2L positioned in a self-reinforced infinite material medium is considered. So a Cartesian coordinate system OXYZ is defined by mod of x less than equals to L on y equals to 0. And a time harmonic longitudinal magnetoelastic plane wave is propagating along y-axis in the positive direction and incident normally on the strip. We consider UVW the displacement components in the direction of X, Y, and Z axis. Deformation conditions, which is defined by equation number 4. Here, x-axis is considered as a plane of the symmetry for self-reinforced material. And here we induced a magnetic field. H is developed due to the application of initial magnetic field, and the magnetic intensity consists both initial and the induced magnetics, which is defined by equation number 5. So these are the B. Now, for normalizing the length components, we consider x equals to capital X by L, y equals to capital Y by L, and by using the time harmonic wave, we will having a equation 7a and 7b, where omega is the frequency, k is the wave number, and c is the wave velocity. So now for the boundary conditions, it is considered that the time harmonic plane wave incident normally on the rigid strip in the direction of positive y-axis, and define the wave in the form of equation number 8. So the diffraction of plane waves from the strip requires the solution of equations 7, these equations, because we need the solution of these equations. So requires the solution of equations 7a and 7b that will satisfy the following boundary conditions, that is equation number 9. So you know the strip is rigid, so the displacement component will be 0 at the strip location, and the total displacement field is defined by u equals to u incident plus u diffracted, and now v equals to the v incident plus v, the diffracted part of the wave. And here I have removed the time factor, which is common in all the variable. So here, what is the diffracted displacement? So the diffracted displacement refers to the displacement field of a wave after it encounters to an obstacle such as a crack or a strip, causing wave scattering and the diffraction. So the solution of equations 7a and 7b may be considered in the form of the equation 10a and 10b. So the exponential part of this, exponential minus nu of y, controls how what we can say, how the displacement field decays as the wave propagates away from the rigid strip. And the sign of zeta x ensures the correct antisymmetric wave response in the horizontal displacement. And the cos zeta of x ensures the correct symmetric wave response in the vertical displacement component. And why these integrals are considered? So these represents the diffraction pattern as a superposition of the multiple wave. So now on substituting these assumed solutions in the equations 7a and 7b back here, we will have the relation as shown in equation number 11a and 11b. Again, there is a tons of mathematics. So because of the time, I'm skipping here. So this work is published recently. So on equating equation 11a and 11b, we will have the equation number 12, and the vertical diffracted displacement on the plane y equals to 0 of the strip is obtained by equation number 13. This was our main motive to calculate this diffraction component. So now the computational results. So for the numerical study of the established analytical result, we consider the elastic constant values for carbon fiber epoxy resin, and for the steel with transversely isotropic self-reinforced geometry, and the other one is the isotropic material. So the considered parameters in this study are, magnetoelastic coupling parameter, wave number, and the phase velocity. In these figures, curve 1 shows results without the magnetoelastic. Curve 1 shows the without the magnetoelastic coupling effect, while curve and 2 and 3 include it in the medium. So the figure shows that as the coupling effect increases, so you can 0, minus 0, 0.4 and 0.8. Yeah, it means that as the coupling effect increases, the diffracted displacement also increases in both sides of the in both inside and the outside of the strip. So this happens in all three materials: carbon, fiber, epoxy resin, steel, and the isotropic material. So the maximum energy at the center and decreases towards the edges, you can see. So now the effect of the wave number. This figure shows the dimensionless wave number increases the diffracted displacement both inside and outside of the strip for all the considered materials. The effect is strongest and reaches the highest value when the infinite medium is steel. You can see here compared to these two materials. So this is the phase velocity. So this figure shows the dimensionless phase velocity increases the diffracted displacement. When comparing figures A, B, and C, it is clear that the effect is stronger when the infinite medium is steel. So what are the key findings for this study? So we have a semicircular displacement profile in the middle. So the displacement forms a semicircle inside the strip with higher values outside, and the maximum energy at the center and the decreases towards the edges. So the diffraction effect increases at the strip edges. And what is the effect of the magnetoelastic coupling? It enhances the diffracted displacement in both isotropic and the self-reinforced material. And for the wave number and the phase velocity, the higher wave number means the higher diffracted displacement, and the higher phase velocity means the stronger diffraction effect. So for the comparative study, steel shows the highest diffracted displacement, and the isotropic material ranks moderate, while carbon fiber epoxy resin is the lowest. So what is the overall conclusion of this study? So we have developed the analytical models for Griffith crack propagation and the wave diffraction, the complex materials, applied integral transform techniques, and the controlled integration methods for precise solutions. And for the application point of view, these findings contribute to the fracture mechanics, ultrasonic, and in the material engineering. And in future, I'm trying to do this study in the experimental way and some multi-layered kind of structures. And for the acknowledgement, institutional support center, I want to give a thanks to my Center for Non-Destructive Evolution, Iowa State University, my collaborators from IIT Dhanbad, and a special thanks for my colleagues, students, and the research teams. And thanks to all attendees for their valuable time and interests. So this talk is basically not from the computer background. So this is basically from applied maths, mechanics. Yeah, now I'm open for the questions.
So thank you. Thank you, Dr. Pulkit Kumar. So I'd like to ask, is there any questions from the audience? You can ask directly, or also like you can type in the chat box, or you can ask directly.
Hello, sir. I have a question, sir.
Yes.
Sir, in one of the slides, you showed the representation using the Fourier analysis. But
Yeah.
for some problems, if we have like singularity problem, like stress fields, which are around the tip of a crack in a solid. So, like there are other ways to represent that using the radial basis functions like Bessel or Hankel functions.
Yes.
So, do they have certain computational or conceptual advantages, or there is some sort of trade-off between the two?
Actually, the thing is that people use some Wiener-Hoff techniques, some Hankel functions, Bessel functions. But when I use this in Fourier transform, I found that the mathematical complexity reduces. So I thought it will be easier to use as compared to the Hankels and the Bessel's functions.
Okay, sir, I got it. The thing is, the thing I was confused about this, like in case of like a crack tips in singularities, this Fourier representation do not really like do a lot of things like the standard Fourier methods. So I thought like to capture the local behaviors, we can use like the Bessel functions and stuffs.
Yeah, we can use, but for the real scenario, because here I'm using a little bit of the approximations, but when we do, because we want to be match this study with the experimental or the numerical way. So if we deal with the some Bessel's function or the Hankel function, then we need to use a lot of the approximations. So I thought if we dealing with the integral transform, so it will be easy because the matching will be good and the results will more accurate as compared to the other methods.
Okay, sir. Thank you so much, sir.
So is there anyone having any questions? So from my side, there is one question actually. Like, so I'm from computer science background, so I would like to ask, like, what is the scope of application of machine learning in elastodynamic problems?
Yeah, the people are using uh, uh, in physics informed neural networks, artificial intelligence, because we are having a lot of data because of the experimental point of view. So we can use here. People are using the machine learning.
Okay, like they are getting some advantages or like
Yeah,
getting going.
definitely they are getting the advantages.
Okay, okay, nice. So again, is there anyone having any questions?
So if there is no question, Kumar, so I think it's a good time to take the group photo. So Dr. Pulkit Kumar, thank you very much for your wonderful talk. I am Sabyasachi Mukhopadhyay, the Vice Chair of IEEE Computer Society Student Branch Chapter, IIT Kharagpur. So I request all the participants to turn on their camera so that we can capture the screenshot. So I am again requesting all the participants to kindly turn on their cameras so that we can proceed for the screenshot, so that we can capture the group photo. So Dr. Pulkit Kumar, are you ready? So we are taking the screenshot of the group photo. Okay, screenshot for the group photo. So Kumar, I am taking it. Okay.
Yeah.
Thank you very much. Thank you all for joining today's session. Thank you very much, Dr.
Wait.
Pulkit Kumar, for sharing his precious time with us.
Thank you.
Kumar,
Thank you
kindly
so
proceed.
much.
Before concluding, like I would like to we would like to give a token of appreciation from our side. It is I'm going to share the screen. So yeah, so this is from our Computer Society SBC IEEE Kharagpur section. So again, I would like to thank Dr. Pulkit Kumar for joining us, for giving a talk on the mathematics, like